Hello all, I'm Naren from School of Chemical and Biotechnology SASTRA. This is a short video series related to the Chemical Engineering Thermodynamics 2 course. We are in lecture 15 part 4. In this short lecture we will see how to relate Gibbs energy of reaction to the equilibrium constant. A quick recap of what we have seen in the previous lecture and we know is the criteria for reaction equilibrium. So the criteria for reaction equilibrium is written as a summation of a weighted quantity of chemical potential. The weightage is in terms of the stoichiometric coefficient nu I, so which is positive for the product species and negative for the reactant species, and this is mu I is the chemical potential of the species in the system. So the chemical potential of the species in the system is also equal to the partial molar Gibbs energy. So eventually we can rewrite the chemical reaction equilibrium criteria as sigma mu I Gi bar equal to 0. Now let's, as we have seen before, let's see how to calculate the Gibbs energy of reaction. Gibbs energy of reaction. So the notation for Gibbs energy of reaction is delta G and with a suffix capital R. So if we keep the reaction scheme like this, wherein A moles of the species capital A and small case b denotes moles of the species B, react to form C moles of C and D moles of D, the Gibbs energy change of reaction is given as the summation of mu I, which is the stoichiometric coefficient, times Gi. Now this Gi is the Gibbs energy of the component the reacting species I in that system at P and T. Note this is its pure component Gibbs energy and not the partial molar Gibbs energy. So this is pure component Gibbs energy of I. So the pure component Gibbs energy of I, when it multiplied by the stoichiometric coefficient, this is obviously the stoichiometric coefficient, or I will say as signed stoichiometric coefficient to denote that it is signed with respect to the reactant and product species. So the product of stoichiometric coefficient times the pure component Gibbs energy of the component in that system, the summation of that denotes the Gibbs energy of the reaction. So we will see how to relate this to the equilibrium criteria. Now to do that, this Gi bar, so Gi bar, which is the partial molar Gibbs energy of component, this is of component I in the system at a given temperature and pressure. We know that this Gi bar is proportional to RT ln Fi cap. Now Fi cap denotes the fugacity of component I in that system. So this is not its pure component fugacity, it's a fugacity of the component in the solution system. So that's why you have this notation of Fi cap. And compare this with the pure component Gibbs energy. So this pure component Gibbs energy can also be written as proportional to RT ln Fi. So this, in this case, this is the pure component Gibbs energy. So this is the pure component Gibbs energy, and this is the fugacity of pure component I at the same temperature and pressure. Now instead of the reaction temperature and pressure, if we do at standard state, suppose if we apply at a standard state condition, so that means if the pure component values are at a standard state, standard state T and pressure. Typically the standard state is denoted by a naught. This could be at 25 degrees Celsius, and the standard state pressure could be at 1 atmosphere or 1 bar. So if we do this pure component at standard state, we just write it by a notation that Gi is naught is equal to RT ln Fi naught. So we are going to take the difference of this equation. The first expression, which is the Gi bar, is the partial molar Gibbs energy of the component in the system, and the second expression of the Gibbs energy of the pure component in the system, but evaluated at the standard state condition. So let's take this. So if Gi bar is proportional to RT ln Fi cap, and this is Gi naught is equal to RT ln Fi naught. If we take difference of these two expressions, we get Gi bar minus Gi naught is equal to RT ln Fi cap minus RT ln Fi naught. So if you can take the difference of log as ratios, RT ln Fi cap divided by Fi naught. Now the next step, that means Gi bar can be written as Gi naught plus RT ln Fi cap divided by Fi naught. So this is the expression we land, wherein the partial molar Gibbs energy of a component in a system can be related to the pure component Gibbs energy at the standard state, and the second term, which has a ratio of RT and ln on the ratio of fugacity of a component in a solution. So that is why this is Fi cap to the fugacity of the pure component, but the pure component is evaluated at the standard state. Now we are going to utilize this expression into the criteria of reaction equilibrium that we saw here. So the criteria for reaction equilibrium, as we know, is sigma mu I Gi bar is equal to 0, and we have here Gi bar is equal to Gi naught, the standard state, plus RT ln Fi cap divided by Fi naught. So let us multiply this equation. We will multiply this equation with the stoichiometric coefficient. So multiplying that with the stoichiometric coefficient, so multiply with the stoichiometric coefficient, we end up as mu I Gi bar is equal to mu I Gi naught plus mu I RT ln Fi cap divided by Fi naught. Now see this term then now denotes the Gibbs energy change of the reaction on summation. So that means now we have to do a summation for all the species. So summation for all species. So this is for one species, but if you do the summation for all the species, we end up like sigma of mu I Gi bar is equal to sigma of mu I Gi naught plus RT is common, so it will come out of summation, and a summation of mu I ln of Fi cap divided by Fi naught. Now this term you can relate it to the Gibbs energy of reaction that you see here. So the summation of the stoichiometric coefficient times the pure component Gibbs energy is related as the Gibbs energy of reaction. So that means this term we can write it as delta Gr. Now because this is evaluated at the standard state, we write it as delta Gr naught plus RT. The second simplification that we do is for the log. Now this term will go as a power for this entire term, because you can just transform by using the principles of logarithm and indices. So this will become ln of fi cap by fi naught, and this whole raised to the stoichiometric coefficient. Now we know that from the equilibrium criteria for reactive systems, this summation is 0. So that means this, by applying here, this will become, so this is from the criteria of reaction equilibrium, we have this to be 0. Eventually that means RT ln RT sigma of ln fi cap by fi naught, the whole raised to the stoichiometric coefficient, is equal to minus delta RGR naught. So I'm just taking the Gibbs energy of reaction to the other side. Now what we have to know is this term. Okay, this term is called as an equilibrium constant. So specifically this can be written as an equilibrium constant Ka, right? So this ratio of ln of fi cap by fi, which is summed up, right? When you sum up the log, it becomes a product. So that would be called as Ka. So let me just write the expression for Ka. So Ka is equal to ln of fi, or ln rather, fi cap by fi naught evaluated at this, and do a summation of this, which eventually leads to a product term, right, of fi cap by fi naught raised to this, and then taking a log. So you can just transform the summation of log to the product rule. So this is what is the ln ki definition. So you can see here this term is denotes Ka. So if you just denote this term as Ka, then that means your expression becomes RT ln Ka is equal to minus delta GR naught. And now this relates the equilibrium constant ln Ka as minus delta GR naught by RT. Right, so this is the expression relating Gibbs energy of reaction, at standard state, so which is delta GR naught, and equilibrium constant. So equilibrium constant Ka. The definition for Ka is then it's a product of fugacity of the component in a reactive system. So that means in a solution raised to the fugacity of the component at the standard state, the whole raised to the respective stoichiometric coefficient. So this term together is denoted by Ka. Now can you guess why it is called A? We could have written this as K for a constant, but can you just think on what is this A denotes here in this constant? That is something to do with this ratio that I would like you to think as part of this video lecture. A is this ratio. This ratio is called A. Right, can you just get what is this ratio? With that, I will take a break of this video. So in this video, we have quickly developed a relation between the equilibrium constant to the standard state Gibbs energy of the reaction. So the Gibbs energy of the reaction towards equilibrium constants. Thank you for watching this video. Bye.